being here today. So as mentioned, we're going to be talking about scaling and visualizing billions of microservices out there. So for everyone not aware, my name is Devin Lawler. I head up sales engineering here at Epsagon. I have nearly a decade of experience architecting both distributed applications and solutions in more traditional on-premises environments, as well as in cloud environments too. Now, I've been working in observability as well as ops and monitoring for a number of years now and truly love working in this space. This here on the side is me about 15 minutes after my wedding wrapped up this past November. Thankfully, that was something we were able to really just eke out before this whole crisis began here. And yeah. So really, we're going to be discussing four main topics today. The architectures of yesteryear and the challenges that those presented, as well as some of the benefits that we saw in those environments too. Getting stuck in visualization hell, if you will, when trying to work with highly complex, highly distributed architectures. The challenges of troubleshooting in distributed environments. And lastly, having easy to implement tracing within these complex environments as well. So architectures of yesteryear, if we think about them, they're really the client server based applications that were extremely easy to visualize, as we can see here. However, with that, it was significantly more difficult to scale and really to be able to quickly push new features or fixes as well. Scaling up was at one point in time really the norm, and scaling out was a rudimentary concept that was oftentimes reserved just for databases. A single component failing was often easy to pinpoint from a resource standpoint. However, that introduced significantly more complexity when it came to implementing an actual fix. So to help keep environments running, we started introducing concepts such as active passive and active deployments for quick remediation during failures. So this architecture, of course, relies on having an active copy of your service with a passive copy waiting to be switched on in the event there's a failure, which is incredibly wasteful and costly. Sure, you could keep that passive node entirely turned off, but that then means a greater period of downtime for any of your end users. Additionally, you have to hope for database consistency and availability within that mix as well. So having helped support and build architectures in the past, I can tell you, or really such architectures in the past, I can tell you that while this sometimes worked, albeit partially or rather albeit painfully and at great expense, updates were themselves oftentimes painful overnight ordeals, with my wife wondering why I was setting a 1 o'clock in the morning alarm to help a customer with a simple update. And outages in the best case meant getting scores of teams involved, from the database administrators to the network engineers. Or in other cases meant you simply had to try and act like the DBA at 3 o'clock in the morning, something I'm far too familiar and completely adept at doing. Now, monoliths, as I mentioned, really did come with their own benefits. While scaling the infrastructure was oftentimes more costly, it was a significantly simpler model. During Black Swan events, you would simply throw infrastructure resources at the problem, while today we're naturally throwing services more times than not at it. Of course, in some lucky cases, you could scale horizontally, but this also required identical copies of an application or a service, which was now wasting precious resources. Additionally, this infrastructure came at a significant cost, and for startups meant making very different and decisive decisions with their roadmaps and even marketing efforts as well. Now, monitoring in these environments could be a little easier, as you could rely purely on bytecode instrumentation or even things like profiling to help discern where problems in the code may lie. And architecture maps oftentimes included only a handful of services at best, maybe a couple of databases and a message queue or bus if you were really leaning on next-gen technologies at the time. Builds and deployments, while time-consuming, were a little simpler in nature as well. So if we roll the clock back about a decade or so, I remember builds being a lengthy overnight process at one of my first companies. We'd start a build at 5 o'clock in the evening and then come in the morning with fingers crossed that it went smoothly. However, rather than our application having dozens, hundreds, or thousands of potential moving parts to consider during a deployment, we're oftentimes just shipping an entire updated package to install to our customers. When the builds worked, we could be reliant on a mostly automated QA process, as both the client and server were packaged together, and we were at least some of the time able to quickly identify a bug. So how did we get to where we are today? Now, an argument could, of course, be made that March 19th, 2006 was a huge catalyst for this. Those of you that are geeky enough to memorize technical trivia will be able to recognize that this was the date we were all introduced to Amazon Web Services. Well, it was extremely costly at the time, and almost no one outside Amazon was running production services on it. AWS was really an absolute game changer. Now, even more so when we consider that most venture capital money was drying up at this point as we were entering the Great Recession, but this also saw some of the largest startups born. So suddenly we were no longer dependent on managing bare metal servers or hypervisors or staffing engineers to be in data centers as applications and services began being lifted and shifted to the cloud. So suddenly infrastructure became code to manage and became yet another point of complexity for engineers to be focused on. So thus the era of DevOps was born. Now this same lift and shift is still common today. And at Epsagon, we see a number of our customers utilizing our platform for hybrid deployments as companies do progress to the cloud and look to identify areas of inefficiencies and errors, something of key importance in the cloud migration journey. Now, from there, we saw the rise in software as a service as payment gateways, authentication, and even databases became commoditized services. This introduction started to allow engineers to begin breaking down the silos within their applications and really start taking advantage of technologies like containers, which really oftentimes were utilized for pre-production and development purposes only. Suddenly, those easy to depict architecture diagrams were beginning to become chaotic rat's nests of interconnected services, databases, message queues, external APIs, and everything else that can really make up applications today. Now, functions as a service then were introduced, and suddenly we stopped having to worry about some of the underlying infrastructure. This allowed us to break things down into even smaller components or become even more polyglot with our approach to writing services. And yet again, more complexity was introduced to the overall application's topography. Now, all of these amazing evolutions that have happened in technology have made our release cycles quicker, our ability to push cool new features to users, or even have dozens of various tests running in parallel. However, this has also introduced significant complexity in troubleshooting, observing, and visualizing our environments. So I'm sure many remember this great visualization from re:Invent a few years back. Netflix gave an overview of just how complex their environment is. And now imagine this up on a dashboard and hoping that you can spot a traffic light change color, or that you can pinpoint an endpoint that wasn't updated for production properly, or any of the dozens of other SLAs you might be tracking for your services. Now, the introduction of containers, abstracted functions as a service, service meshes, managed NoSQL, and relational databases solving different problems has certainly helped to speed up our development velocity. But oftentimes what starts off as potentially a simple to solve business problem becomes a highly distributed environment with complex auto-generated visualizations hampering your troubleshooting initiatives. Now, these highly distributed modern applications are more typical than ever today. So rather than being built in data centers with hardware owned or leased by companies, or as legacy client-server applications, they're built in the cloud. These modern applications are highly distributed, of course. That is, the application code is broken into even smaller, more lightweight services, which can almost be thought of as mini apps themselves, each of them running independently of one another. Now, there is no one single monolithic bundle of code for the application either. So telemetry and metric data is no longer simple to infer application health and availability from each of these components, as they can suffer varying degrees of potential issues or latency. There's no longer just a few application events, but many. So really the days of a Windows-styled event manager being useful are really long gone at this point. And in fact, services can be generating billions of metrics in various telemetry data points. So the events themselves can also be asynchronous. That is, there's no clear, straightforward timeline of them that you can easily track down. And modern applications can be problematic for both engineering and DevOps alike. Unfortunately for engineering and DevOps, building and monitoring, troubleshooting, and visualizing modern applications is not as straightforward as saying, let's just move to the cloud, we can save on costs, or We can use this new cool caching layer that's going to help reduce latency by 15%. Troubleshooting production issues for microservices and serverless components requires more than basic logs and metrics here, which are simply not the right tools for these highly distributed environments. Remember when we had to only deal with maybe a handful of log files across a set of services, and even that presented many challenges as well. Additionally, when we consider that 80% of production issues will be found by customers rather than ops or engineering, observability is absolutely critical to providing an above and beyond customer experience for our end users and requires a shift in mindset to becoming more proactive rather than simply reactive. You have to know whether the application is working properly and be able to pinpoint exactly which component within the architecture is failing. So you have to enable developer velocity and easily visualize what's currently running in production to rapidly build new cloud services and save on development costs. So let's change gears and think about troubleshooting in these distributed applications and environments as well. So naturally, issues can arise in many different forms, but did they truly start where an alert shows, or could they have begun earlier in the stack? Now, how can we validate that there wasn't malformed data being sent to our Lambda from a service earlier in the flow, perhaps? Or how can we be sure that an outage we're seeing is in fact due to our service and not really a third-party API that's downstream? As an engineer, do we then dive into logs across dozens and dozens to thousands and billions of services, hoping to spot the proverbial needle in the haystack? How often do we find ourselves quickly scrolling over dozens or hundreds or thousands of log lines, hoping to spot an outlier? Similarly, how often have we sat and watched the live tail of the logs flowing through? What if we could have that same view, but with the exact path a request is taking through an individual service as well as those components? Now, really being buried by logs is not a fun problem or a fun endeavor to be undertaking. So really, something is missing here. With just logs available to you, a problem will inevitably be missed on the first go around and will undoubtedly become a massive time suck for you as well. And while log aggregators help bridge the gap of centralization, help bridge the gap of centralization on their own, logs still lack the context to an event or a metric that you're tracking. So logs are also heavy and oftentimes lack structures that are even more challenging to determine what is wrong. Now, let's change gears a little and talk about distributed tracing as well as its origins and how this can also help with visualizing and troubleshooting in these complex environments as well. So I'm sure everyone here today has been hearing a lot about distributed tracing and tracing in general lately. Now, many vendors out there offer some form of distributed tracing, and even many service meshes are now building in support for it. There are also dozens of open source solutions, some of which have been born out of huge enterprises today. However, where did it begin and why? So distributed tracing was born out of Google over a decade ago, and it's there to allow engineers to trace the specific path a request makes through services. And in effect, it helps shine a light on that needle in the haystack that logging or metrics alone can miss. Just because an application is made up of 15,000 services doesn't mean a request will naturally travel through every single one of them. At best, it will travel through a fraction of those services. And beyond this, distributed tracing becomes a fantastic way to start determining where in your stack time is being spent. If it's taking 2 seconds for a response, is that due to time being spent in a database query? Or is the service taxed on memory and unable to be as performant as we would like? With distributed tracing, you then had frameworks like Jaeger and Zipkin and many more come about too. So some order was brought to this chaotic landscape with the introduction of open tracing and open telemetry. And these are standards and frameworks to be followed and utilized, though while immensely helpful in pinpointing issues in highly distributed environments, they come with significant development efforts. That's slowing down that key developer velocity that we really hope for. Furthermore, these oftentimes lack the visualizations necessary to track the exact path a request travels, limiting you to flame or waterfall graphs for troubleshooting. Additionally, they lack key context with metrics and logs and don't necessarily provide you with the ability to search for specific data within your APIs as well. As I mentioned, these standards also slow down developers as they have to pause to remember to account for defining spans and segments within your services, which becomes a truly costly endeavor for anyone that's had to undertake this. The traditional mechanism utilizing headers propagating between services can also introduce latency on their own or provide an incomplete picture if those headers are stripped out and lost along the way. All of this data must also be kept somewhere, and with open standards, you're suddenly now running and scaling an observability platform internally as well. So let's bring things back to how to best troubleshoot in these large scale environments, as well as how to visualize those key components. At Epsagon, we believe in lightweight, easy to implement tracing with out of the box visualizations that do provide context, not only between a trace itself, but also the metadata, metrics, as well as CloudWatch logs all in one unified view. So whether a trace begins from an S3 file drop, which triggers a Lambda, or the usual web request, you want to see that end-to-end picture of exactly what path users' request traveled. Additionally, when an issue arises, we want to provide our users with flexibility of accessing the full payload. So if a user happens to open a ticket, I can then search for either an email address, a user ID, some sort of GUID to tie back to that user, or I can pinpoint exactly why a failure has occurred. Additionally, if I need to start seeing performance for an endpoint that's being called, I really want to be able to filter and search just based upon that specific endpoint. Lastly, we want to provide context to what's being seen within the logs. So when an error occurs, we can present the metrics, events, logs, and tracing, really the three pillars of observability melt, all within one unified view. This, of course, would be a micro view of a trace that we can see here, showing the exact end-to-end flow of every service and component touched along the way. However, what if you've added a new service into the mix, or there's a new large deployment being pushed? We also want to provide engineers with a live tail experience to quickly and easily see trace data as it's flowing in. Smart alerting strategies based on thresholds or specific errors can, of course, alleviate this need in most cases. However, if you need to quickly validate that an issue has been remediated, this can be a tremendously helpful mechanism. And this helps to change gears away from simple service maps to a live view as to what's happening within your environment. Additionally, to cut down on the noise from services or applications, we can filter this view on down to a specific entity or ensure that we're only showing traces based upon specific criteria or thresholds, like return codes or latency exceeding a given threshold. As sampling can be entirely disabled ad hoc, this can also mean you get a complete picture of every single trace in every single transaction, which can be absolutely critical when you're trying to spot an issue across potentially billions of services that are out there. Now, traces within our environment, of course, can get complex as well, but with smart visualization strategies, we've cut down on the number of messy, intertwined rat nest components that are seen here. However, even in those large-scale environments, these too can get very, very complex. So in large-scale environments, as we can see here, we want to be able to provide our users with the ability to succinctly go from viewing the entire architecture to zooming in and filtering on specific components. So engineers also expect actionable data within these complex visualizations and maps. And as we zoom in or filter on specific components, engineers should have the ability to start seeing that latency between those components in areas where thresholds have been crossed. Metrics should also be presented to start providing context to these issues or alerts that are going on as well. Or when we identify an issue within a service or an application, we can focus the visualization on down to narrowly scope the service so that the filter applied brings it down to the immediate up and downstream components to really take out the guesswork in determining the impact of an outage, what latency is being seen, or understanding precisely what could be leading to an uptick in errors that are suddenly being reported for an individual component. Now, without smart filtering abilities, an architecture map becomes nothing more than a beautiful exercise in chaos theory, as you hope to spot some grain of metric goodness that can help troubleshoot along the way. So, of course, we also want to visualize latency within these views too. So in highly complex distributed environments, we want to be able to narrow and pinpoint down what service and what specific component time is being spent within. This is equally critical or crucial in cloud transformations and for continued service excellence. If we think about it, 40% of users have been found to bounce or leave a site or application that sees latency of 3 seconds or greater. And this becomes absolutely crucial in saving revenue and ensuring a satisfactory end user experience. So service maps can be a one-stop shop for pinpointing where time is being spent, often within these large-scale applications to help determine where and when inefficiencies may be occurring. So again, tracing solutions should narrowly pinpoint where time in the code is being spent. Is a significant portion of time being spent waiting for an external API to respond, or perhaps we have an inefficient database call, so an N+1 error that needs to be refactored. These waterfall visualizations make it easy, and at Epsagon, our waterfall visualizations can also provide you with that rich context, the header metadata, to really begin doing some real-time troubleshooting. So in summary here, we know that applications of yesteryear allowed for more easy monitoring and visualizations within these environments. However, these monoliths are more difficult than ever to scale, fix, and continuously develop new features for. Distributed architectures come with their own unique benefits and, of course, challenges as well. Observability through metrics like throughput or simply seeing response time aren't enough now to determine where the issue is and don't provide us with the value necessary to keep our environments healthy. Tracing with context, on the other hand, does help to tell a story of where, when, and why an issue has occurred, and really helps to pinpoint errors and shift our mindset away from simply being reactive to issues to being proactive and having keen alerting strategies with succinct SLAs to be tracked, all within a unified platform as well. So at Epsagon, our ethos is that tracing should be easy to implement. It should be automated and it should be secure. So we're providing APM with out-of-the-box visualizations and service maps to really help paint an end-to-end picture of your distributed environments and ensure that we can pinpoint exactly where and why an issue occurs. Security is also top of mind with all of this as well, knowing the nature of many of our customers' data. So we also ensure that all data is encrypted, of course, in transit, but also at rest. And security being top of mind, we ensure that we are HIPAA as well as GDPR and SOC 2 compliant as well. So thank you all so much for your time today. From all of us here, we hope you stay safe and healthy through this trying time as well. So it looks like we had a couple of questions that came through here too. I see, can you monitor services running in ECS or Fargate or in more traditional Kubernetes environments? So yes, we can. Whether a service is running in, again, ECS or Fargate, or if it's EKS, so a managed instance of Kubernetes or a self-hosted instance that's running on-prem or in the cloud, we can indeed monitor those services. And in regards to another question, does Epsagon automatically build service maps or require manual tagging to build relationships? We do not require any manual tagging whatsoever. So all service maps, all visualizations within our platform are 100% automated. So there's no need to have to stitch together complex connections reliant on tags or anything like that. Kind of a loaded question, is it better than Dynatrace or similar? So we definitely take a very different approach than a Dynatrace takes. Dynatrace is a little bit more reliant on, kind of like I was talking about before, with bytecode instrumentation, which I would still say is absolutely critical and necessary in monolithic environments. Our approach is very, very different than that. We're not reliant on bytecode instrumentation or a single unified agent like Dynatrace is. We automate the distributed tracing across services. So instead of introducing latency by hooking into an application, distributed tracing is significantly more lightweight. It doesn't have the same kind of overhead that a Dynatrace or a similar type product could have as well. So if those are all of the questions, I certainly thank everyone again for their time here today. If you have any other questions, just absolutely do feel free to reach out to us at epsagon.com and we can handle those as they come up.